evening, or even morning. We have geotechs, geologists, and engineers from all over joining us today. Thank you so much for your interest in this first of what we hope are several technical webinars. We hope these lectures contribute to bringing the geotech tailings technical community together and to collaborate. Hopes are we can learn from each other and push the industry to the state of art, whatever the consultancy firm or mining company we come from. I would also like to mention young professionals and students that have logged in today. They will be a key aspect in the industry development, given the shortage it is currently facing. For today, we are honoured to have Dr. Paul Mayne sharing with us his experience with soil sampling for advanced laboratory testing. At the end of the lecture, we'll have some time for questions and answers. Paul has been active in geotechnics for 46 years, with the past 32 years associated with the Georgia Institute of Technology. He has a total of 370 publications and has participated in over 120 continuing education courses. He is active in national and international professional organizations. On a personal note, Paul is married with one daughter and plays bass guitar. I haven't heard him yet, so I can't say much, but hopefully I'll get the chance to. So without further ado, I'll leave you to it. Paul, please go ahead. All yours.
Thank you, Gail. Thank you for having me today. And today we'll talk about soil sampling for advanced laboratory testing. Next. So we have many different laboratory tests. We sort of grew up in geotechnics by thinking we could go out into the field and take samples, bring those samples back to the lab, and then we could run a whole suite of different tests to tell us what the properties, characteristics, and features of the soil to help us do engineering design. So here's a select few of those. Next. So when we take a sample out of the ground, we have the sample is the large tube size shown on the left side of the screen. We are going to cut small specimens from the large sample. And these vary in size. Some of them are just small. I call them cookie size. They're maybe 25 millimeters thick by 75 millimeters in diameter for a one-dimensional consolidation test. But others of them might be more like 150 millimeters high and 75 millimeters in diameter for, say, a triaxial test. But why advanced laboratory testing, these are some of the tests that we're talking about. Direct simple shear, resonant column, direct shear, tests that give us strength, compressibility parameters, permeability, and other geoparameters. Next. To do that, we have to create a borehole. And many times it's just efficient to have the drill rig mounted on a truck or a trailer or some tracked vehicle, depending on the accessibility of the ground. Next. There's also percussive drilling. There's no samples taken, so this is just a way to make a borehole, for example, when we want to place dynamite for excavating rock. Next. So we have different types of borehole methods. We have soil drilling methods where we use solid flight augers. Those are kind of awkward because you have to remove them from the borehole each time you want to take a sample. We have hollow stem augers. Those are probably the most common here in the United States of America. You see a picture of a truck-mounted rig with hollow stem augers here in Carson City, Nevada. We have rotary wash techniques. That's a good method, but it requires adding water or drilling fluid. We have wireline drilling methods. We also have continuous push samples. I just mentioned the percussive methods here in the slide before this one. And then we have sonic drilling methods. So we have different ways of making boreholes, but in order to get undisturbed samples for advanced lab testing, we pretty much are going to be restricted to using hollow stem augers, rotary wash borings, and wireline drilling. Next. So there's different types of soil sample. There are disturbed samples. Some of those are listed right here. Probably the most famous one is a drive sample known as a split barrel or split spoon sample. We have, today we have continuous disturbed samples. You might know these as geoprobe or AMS probe, power probes. And then we have the undisturbed samples, and those include the list down there that we're going to run through here shortly. So let's move to the next slide. So bulk sampling, I mean, this is just if you want some of the material itself to check for some classification specifications. For example, it has to have a certain grain size distribution. It cannot have more than so many % fines content. It needs certain plasticity characteristics. Maybe you'd like to compact this. So these are just large samples of the material itself, but not in a pristine condition, not with all the fabric and structure of a natural soil. So these are not appropriate for advanced laboratory testing. Next. As I mentioned, probably the most common sample is the split barrel or split spoon sample. This is taken during the standard penetration test. That's given by ASTM-D 1586. And essentially, it's a hollow, thick tube that we pound into the ground. We count the number of blows to drive this a certain distance with a drop hammer system. But the cyclic loading, the thickness of the wall all make these very disturbed. So it's not appropriate to use split barrel or split spoon samples for advanced lab testing. Next. One way to measure that is what's called the area ratio of the sampler. There's the equation. I took this as an excerpt right out of the book, Terzaghi, Peck, and Mesri. And you can see there that the standard penetration test with the split spoon gives you an area ratio of 112%. Well, that's way too high. As they show here, the value should not exceed about 20% if the disturbance is to be nominal. Next. So we have a series of types of tube samplers that we call undisturbed tube samples. And the thin wall Shelby tube is the most common. It's given by ASTM-D 1587. It's a nominal 3-inch outside diameter with a 2.8-inch inside diameter. And it's used to capture undisturbed samples of soft to firm silts and clays, perhaps clay and silty sands. They're typically about 30 inches long. They're typically made out of carbon steel, but they can also be made out of brass or stainless, especially if you're working in a saltwater environment. You don't want the material to be corroding after you've taken your sample. However, this is like the bare minimum for the qualification to call it as undisturbed. Next. So in the USA, I say undisturbed sampling, and most of the geoengineers in this country would say Shelby tube. Well, okay. Next. We do have some states that do not have the best practice. What they do is they use a tube sampler to capture the material, and then because they like to reuse their tubes to save a couple of pennies, they'll extrude the sample in the field and wrap it in tinfoil or aluminum foil. This is really poor practice. Undisturbed soil samples must be maintained in their tubes and extruded only when we're trimming specimens just before the testing is to commence. So this is not very good practice. Next. So undisturbed thin wall tube samples come in a variety of sizes. They do make them as small as 50 millimeters. I would suggest that you use at least something on the order of 78 millimeters or larger. There's one that's popular with the U.S. Army Corps of Engineers called a Gus sampler, Greg undisturbed sample. Gus has 125 millimeter diameter. So usually the rule of thumb is larger diameter means better quality sample. Now, once you take a sample of the soil, we certainly don't want any changes in water content, moisture. So it's very common to seal the samples up using liquid paraffin or wax. We also have these special plastic sealants with a wing nut and an O-ring. In some cases, just to be on the safe side, we do both. We use liquid wax and we use these plastic O-ring sealants. Next. And then we have a whole family of special samplers. I didn't really have the time to go through collecting information about all of them, but we'll look a little bit about some comparisons a little later on. But piston sampler is like a Shelby tube, but it has a little piston at the back end that applies a slight vacuum when you're trying to retrieve the sample rather than have it fall back into the borehole. So we don't want that to happen. But we have special samplers like Sherbrooke, Laval samplers named after the universities in Quebec. NGI stands for Norwegian Geotechnical Institute. We have Japanese samplers. And so these are intended to get the best quality of the in situ soil material for the lab testing. They also help provide the least amount of disturbance so that we get the best results in the triaxial tests and the consolidation. Next. Here's a little more detail on the piston sampler. Some of these are also known as Osterberg samplers and Vorschleff samplers. And so they're very useful in soft soils. You can distinguish between a free-headed and fixed piston head. These provide vacuums, again, at the back end to help increase sample recovery. I guess the unfortunate part about many of these samples, they all more or less look the same. Most of our boreholes are circular, done by rotary drilling. So all the tube samplers they all have that common feature that they're long cylindrical tubes with different wall thicknesses. And so there's that similarity there. Next. We have something called a pitcher sampler and another sampler called a Denison sampler. And this is when the soil is rather hard and hard to get out, very stiff material, stiff to hard clays and even soft rocks. And we still need to get a sample. So we have a tube within a tube, and the inner tube retains the soil, and the outer tube is rotated to sort of cut into the material as we advance into the ground to get our sample. So if it's particularly hard, you may want to consider using one of these two types of samplers. Next. We do have today direct push borehole methods, and these are very interesting because we do get continuous samples. So there's a whole fleet of groups, the geoprobe, power probe, and similar types of devices. It's a one-person operation. The operator can go at least 30 meters, even as deep as 45 meters, all by him or herself, and collect continuous samples. Now they are disturbed, but the diameters can be anywhere from, say, 25 millimeters to 75 millimeters. And it's sort of like a steel mandrel with a plastic lining that captures all the soil, so you can follow every millimeter all the way down to, again, whatever depth, 45 meters you're going. And so that's advantageous to see all the soil. But they are disturbed. Next. And here's some pictures of them. Here's the different types that they have. On the right-hand side, you can see here the plastic tubes that are holding the soil. I believe these were taken right outside of civil engineering at Georgia Tech. And you could follow along, see the changes in color. And you could do simple tests such as, percent fines or possibly gradation, resistivity, water contents, but you cannot do advanced lab testing. Next. If you do need to get continuous undisturbed samples, what's a very popular method in Holland, in the Netherlands, is the Begeman sampler. So here, these are continuous samples. Some of the specimens have been removed for testing already, but you can follow along centimeter by centimeter all the way down the boring to see all of the soil. And I'm not aware that this is in North America, but it seemed like this would be a good device to bring over to South and Central and North America for use here. Next. It's not the primary part of cone penetration testing, because we're trying to get continuous readings of cone resistance, sleeve friction, and pore pressure. But if need be, you can have a sample taken at a specific elevation. And so there are some CPT soil samplers. Again, I would say these are more on the disturbed region, so you can at least look at the material. Perhaps you just need to look and determine what the fines content is, because you're doing a soil liquefaction evaluation. Next. Now, once you take the samples, you have to protect them. You can't just take the samples, pull them to the ground and not let them sit and desiccate in the hot sun. They're going to dry out. They're going to change in moisture, water content. This is all very, very important to keep everything just as it was in the ground. And many times, even the soft clays and the loose sands have been there for thousands of years, 10,000 years since the last melting of the last big ice age. And so we have to protect these. And so obviously the samples have to be identified and marked, what depth they came from, hopefully what kind of soil they are, which boring they were come. Hopefully you're going to do that. But it's very common to put the samples, if they're split spoon samples, in a glass jar or a plastic jar, and then each of those samples are held in order in some sort of matrix array, based on where they were taken in the depths and the boreholes. But it's very important for all the samples, the undisturbed samples, the Shelby tubes, the piston samplers, the Begeman samples, all of those have to be protected from sun. So you don't want them to get too hot. You don't want them to freeze overnight. You don't want them to dry out. So you have to protect them against the temperature. And then when you transport them from the field back to the laboratory, you don't want to jostle them up. You don't want to shake them and expose them to excessive vibrations, because this is all going to change their characteristics, and then you won't be measuring what's really there. So that's very important. Next. So there are samples for rock. So to take rock samples, we need a core barrel. And there's different kinds of core barrels. Over on the right-hand side, you'll see a single barrel type. It just has one tube. That tube rotates to collect a sample of rock. Well, that's easy, but the problem there is this tube is going to spin at, say, 1,000 RPM, and it's going to subject the rock that you just captured to thermal changes. A lot of friction. It's going to heat up. That's going to want to change the characteristic of the rock. So you've got to do something better. So none of these core barrels are really recommended for soil. So we don't want this for soil, but for rock, we would want to go to the next slide, which is a double tube core barrel. That's considered the minimum standard of practice in the United States. You have a tube within a tube. The outer tube rotates and has a bit on the front end to cut into the rock. Again, you can cut into soil. And then the inner tube has the soil, is a place to collect the rock that you've captured to protect it until you get it back out. Because again, we don't want to expose it to excessive temperatures, heat, friction, vibration. So we're trying to protect it. Next, there's also a triple tube core barrel. And in that case, it's even better. It's a way to minimize the friction and the vibration and so forth. However, it comes with the complexity that it requires a special type of a driller to operate this and collect samples in the field. So that's a special case. Next. So why are core samples of soil not appropriate? Well, specifically for advanced lab testing. Well, core samples using rotary wash drilling and wireline, they adding water or drilling fluids to advance the borehole. So we're not quite sure what the natural moisture content is if you were adding a lot of water and not taking the samples within the standard piston, Osterberg, Vorschleff type samples. So we don't want to change the in situ water content. The core barrels do not prevent swelling or consolidation. That's again the purpose of these special tube samplers that we mentioned here early. So we want to maintain the in situ density and the in situ unit weight. And advanced soil tests such as triaxial consolidation, resonant column, and simple shear, you want to run those at the same in-place density, water content, porosity, the same fabric. We don't want to change that. We're trying to investigate and determine the properties in situ. Next. Some people like to use stress paths to describe how the sampling affects is affected by disturbance effects. And so if you read the Casa Grande lecture 2003 by Chuck Ladd and Don DeGroot, they'll take you on a series of stress paths, starting with one, the in situ K-naught condition, and why we want to reconsolidate to the in situ effective vertical stress, in situ effective horizontal stress. But if you were to run a lesser kind of test, you could see that there's quite a series of load and unload cycles before we run those tests. So perhaps maybe not the best, but I might encourage you to read that paper by Ladd and DeGroot. Next. Let's look at some of the effects of sample disturbance. So this is a famous test site in the United Kingdom It's their national test site for the Brits. It's called Bothkenner clay, and Professor Tanaka went and took different kinds of samples and subjected them to various types of strength tests. And so here you can see this is the same material at about the same depth. That's about 11, 12, 13 meters deep. And they're running unconfined compression tests. And the lowest sample there, I don't have a pointer, but in the open squares, ELE 100 is a 100 millimeter diameter sample, very similar to a Shelby tube. Shelby tube's more like 78 millimeter. But you see the stress strain curve's much flatter, and it peaks out at only about 50 kPa versus a JPN, which is a Japanese sampler shown by the black circles, and the Laval sampler, which is shown by little X's. Both of those show a much, much stiffer soil, so the modulus is much higher, and they peak more around 70 kPa. So that's a big difference. That's a big difference. Next. And so some of this refers to the different outside diameter OD, inside diameter ID, the length, the wall thickness, whether or not the sampler has a piston. And so Professor Tanaka went and did some comparisons between the Japanese JPN sampler, Laval sampler, Shelby, the Norwegian Geotechnical Institute 54 millimeter diameter, ELE 100, Sherbrooke, NGI 95, and a split barrel sampler just because it's so common. So let's look at some results. There are other samplers, and I've listed some of those right below this table in blue. Professor Tanaka didn't attempt to use all those samplers, but he has a pretty good selection right up here now. So let's go to the next slide and look at some of the results. Oh, sorry. Here's some pictures that we have. So on the right, we have a sort of a Sherbrooke sampler. Those are quite large, probably the largest, and so more complicated, but give probably the best results. And then a modified, an SGI type sampler on the left. Okay, next. So here we go. Here we have a Shelby tube sample and a ELE. And you can see they both give fairly similar results. They're showing the Shelby is giving an undrained shear strength of 18 kPa at peak, and the ELE is given a slightly lower at 15.5 kilopascal. And you see the stress strain curves very similar too. Next. Well, if we compare those with some of the higher quality samples, you see they're very, very different. I mean, the Sherbrooke is considered probably the best quality sampler you can get, 350 millimeter diameter. The undrained shear strength is 38 kPa, 38 versus the ELE at 15.5. So, gee whiz, that's more than a factor of 2. And you can see some of the intermediate samplers are also showing fairly high undrained shear strength. So there's a big difference in the quality of the sample. And so you have to be aware of this, because otherwise you're going to be getting the wrong answer, making the wrong decisions about your project if you're not able to properly capture the undrained shear strength profile of the clay soils at your site. Next. Here's another example. This is Ariake clay from Japan, and you can see the ELE are the blue dots on the left, and the JPN, the Japanese sampler, are the yellow dots, and you see the stress strain curves, and the top of the stress strain curve, the maximum value would be the undrained shear strength, or I guess this is, yeah, is that shear stress? Yeah, divided by 2. So they're very different. The good news is if you plot them in an effective stress diagram, they both come to the same effective stress strength envelope. So that's the good news. Let's look at another example like this. Here we are. Tom Lune has a paper in the Canadian Geotechnical Journal, and this is one of the Norwegian clays. He's taken 3 samples at 6 meters depth, and these are the 54 millimeter tube is the least of those methods. The 75 millimeter tube's a little bit better, and then what they call a block sample, shown by the blue dots, blue symbols. And again, you see we get different stress, strain, strength curves. But again, the good news is if we're measuring pore pressures, we're all going to end up at the same effective stress strength envelope. In this case, all 3 methods show that the clay has a C prime equals to 0, and the effective friction angle phi prime equals 34.5 degrees. So that's good news. Next, okay. Now, what about sample disturbance effects on consolidation testing? There are many, many papers written about this. I just happened to pick a couple of recent references on this. Don DeGroot, 2005, Melissa Landon, 2007. And I guess it would have been better if this figure was in color so we could separate them out. But we have a Sherbrooke block sampler, we have a fixed piston, and we have a free piston. So the best is the Sherbrooke, next best is fixed piston, and the weakest of the 3 would be the free piston. What happens in consolidation testing is poor quality samples tend to cause disturbance that lowers the apparent pre-consolidation stress. So that's not going to be good. I mean, if you're trying to do a settlement analysis of an embankment on clay or a footing settlement calculation, you're going to be off in your evaluation because you have a poor quality sample. So that's why you want to get high quality samples. We don't want to require the owner to do ground modification when none is really needed. So there's another. We don't want somebody driving pile foundations when they could put their building on shallow spread footings. But these are all the effects of poor quality sampling and testing. Sample disturbance also lowers the value of the virgin compression index, C sub C. So these are all very important. Next. What's the condition of the laboratory equipment? You know, I have people, oh, it's the lab told us one thing and the field test told us something different. But, you know, geotechnical engineers are famous for buying a piece of equipment and then holding on to it for 4 or 5 decades. They just won't give it up. Yeah, maybe it still works, but is it really the quality that we want in 2022? Maybe not. Is your lab look like this, all black and white, old equipment that's been handed down, you know, decade after decade? Is it current? Is it automated? Do you get reasonable results? Has the equipment been maintained? Newer equipment, you know, we've improved on load cells. And so, yeah, so here's the new soils lab, you know, the modern laboratory 2022. It's all automated. You still need a technician to properly cut, trim specimens from the large sample, mount them in the triaxial, mount them in the direct shear machine, the mount them in the resonant column device, and then once they're in there, the computer controls all the tests, takes all the data, collects all the data systematically, and then even you can allow the computer to analyze the results, help you to do that. So this is where you should be today. Next. So I thought I'd do a little case study. I got invited by Harry Poulos to come down to Australia some years ago, And he says, we have a project up between Sydney and Brisbane, and we have this very soft clay. You can see it there. It's between 2 meters and 10 meters. And as the question was, is it normally consolidated? Because if it was going to require a lot of ground modification to accelerate drainage and make the ground stable for a large embankment for a roadway. And so the question was, they had recently conducted some piezo cones. And so they said, well, there was a laboratory before we got involved that reported just in a table some values. So I said, okay, let's look at that. Next. And here's what the previous lab showed. They showed that they had 4 samples in the soft clay. Those are the first 4 dots. And then there's a lower clay, stiff, not so much of a problem, but below 20 meters. So, but the upper, say 10 to 14 meters had a very soft clay, and they said, these are the results we got from the lab. And I said, okay, well, it doesn't look that good. Let's look at what the piezo cone said. Next. Well, the piezo cone, you can use the readings to determine preconsolidation stress also. And so we have, if we take 1/3 of the net cone resistance, or roughly 1/2 of the excess pore pressure, we can get an idea where the preconsolidation stress lies. So we did that for the sounding that I showed two slides ago, and that gives to the next figure. And there you go. You see, it's not. It's showing the brown line is the current effective vertical stress. And then the purple dots are 1/3 of Q net, and the green dots are 53% of delta U. So they're suggesting that the OCRs are in the range of 1.5 to 3. It's not normally consolidated, so that helps them in construction, because they're trying to put say a 6 meter to 10 meter high embankment on this soft ground, and they want some stability, some leeway before it's forced to become normally consolidated. So the piezo cone's showing something different than what the lab's showing. So I said, well, let me see the actual lab results. So they said, well, we'll have to dig through the files, and this is what we came up with. So I found the raw data. They found it, gave it to me, and I plotted it up. And here's my consolidation data. Here's the effective vertical stress shown as a green arrow, and there's their interpretation of preconsolidation of 37 kPa. And frankly, I don't see it. I'm not sure why the blue dots are the consolidation test, why that drops down and goes back up. But let's look at the next one. Here we go. Here's the effective vertical stress, and the curve doesn't even start at that point. And then they're interpreting a preconsolidation stress of 50 kPa, and I don't see it. I mean, that's the first load increment they put on there. So I'm not feeling very comfortable about the laboratory, the quality of the lab, and the quality of the samples in this case. Next. Here's another example. This is the 3rd sample at 7.2 meters. And you can see here they're interpreting the effective vertical stress is higher than the preconsolidation stress. But I would say that the sample is either got a lot of disturbance effects, and or the lab equipment is out of calibration and needs to either be better maintained or recalibrated or replaced with newer equipment. Would probably be a good suggestion too. Let's move on to the next one. Now, in this case, we're down in the stiff clay, down around 14.7 meters. And you can see here that we have a reasonable curve, and the preconsolidation stress is indeed greater than the effective vertical stress. And so that made sense, but that's not the problem area. That just shows that it's possible maybe to get some good results here. So let's move on. This is still the same case study. You can also use the vein shear test, to get an idea of the preconsolidation stress. So this originally came from a paper that Jim Mitchell and I wrote in the Canadian Geotechnical Journal some years ago. But the preconsolidation stress normalized by the vein shear strength, the raw vein shear strength, not corrected, decreases with plasticity index of the clay. And it turns out in the soft clay, we do have some vein shear tests, and we do have the plasticity index. So I went and used that and went to the next slide. And the vein shear, the vein shear agrees with the piezo cone. It's lightly over consolidated soil. See that we have 3 orange dots that more or less agree with the 1/3 Q net or 53% of delta U. And they're suggesting that this is a lightly over consolidated clay. And so I think that's where we left it when I finished my month as a visiting senior consultant with Coffee and Partners. After that, they set up a major national test site. The site's called Ballina. It's, again, south of Brisbane, headed towards Sydney. And in geotechnique, there's 2 fairly recent papers, 2016, 2018 vintage. You can see there. And they ran way more consolidation tests. You can see that the OCRs are, in fact, 1.5 to 3. So I think even though we had much less data to work with before this full extensive site characterization, we were on the right mark with that, and the older laboratory results are still to be questioned. Okay, let's move on. So sample disturbance. On the left side, we have photoelasticity, an attempt to use that to quantify sample disturbance. And you can see that there's quite a bit of disturbance in the soil around that sampler, shown by the 2 black lines. The 3 figures on the right-hand side are using X-ray to try to quantify. And you can see perhaps the sample in the middle of the 3 of those is probably the one that has the least amount of sample disturbance. The one on the far right, you can see that there's some side friction where the ends of the little layering, the fabric in the soil are starting to catch on the sides due to friction and get pulled up. So that's obviously something undesirable. And maybe you want to trim a sample towards the center, cut a specimen from the center of that. And then the one on the leftmost of those 3, you can see there's a lot of problems, shearing, distortion. You're changing it. It's not the soil that's in the ground. It's getting all remolded and changed, and that's not good for what you're trying to do as a geoengineer. Next. So it's not that expensive. We've done this at Georgia Tech. I think it costs Professor Carlos Santamarina something on the order of $15 per sample to have them x-rayed, and then you can find out, what kind of situation you're getting. Do they have cracks and fissures? Are there stones or gravels or shells in the sample that you collected? Because you don't want to get those in the middle of your triaxial specimen, because it's going to kind of change the stress path and make a poor result at the far end. And so it's very inexpensive. I want to say the state of New York DOT, Department of Transportation, requires you to do radiography on every undisturbed sample before you cut specimens for lab testing. They don't want you to waste their money running tests that aren't going to be able to be figured out. Next. This is a famous set of figures from Vorschleff's famous book on sampling. This is all the same soil. It's a varve clay at the same depths. And I think you can see that there's a big difference. Sampler A has done the best job. Sampler B, well, there's a lot of side shear friction, not so good. And sample C, wow, it's almost, you know, getting totally remolded. So same soil, but all going to give you a different picture when you're on the lab tests. So sample disturbance is very important. So we can quantify sample disturbance. There's two popular methods. One is the NGI rating. That's delta E, the void rate, change in void ratio normalized by the initial void ratio to reattain the in situ effective vertical stress. And then you can see you could grade that from excellent to very good to fair to poor to very poor. And then another one called the SQD, which is sample quality designation. This is in the book Terzaghi, Peck, and Mesri. And in that case, it's the same information, but you measure the volumetric strain, delta E over 1 plus E naught, in order to reach sigma V naught prime. And so again, you get a grading. And so what can you do with that grading? Well, if we move to the next slide, here's an example using consolidation tests. So here we have 4 different types of samples that were subjected to one-dimensional consolidation. So on the left side is the grading. So the yellow dots are the block sample. That's like a Sherbrooke type sampler. That's the best quality, followed by fixed piston, which are the solid diamonds. The free piston, which is shown by the shaded triangle, and then a split spoon shown by an open triangle. So the split spoon is obviously the worst sample, and that's found to be in the poor to very poor quality rating if you're following on the left-hand side. And as we mentioned earlier, that's going to tend to reduce the pre-consolidation stress. It looks like based on the split spoon samples alone, you're just getting about 100, little more than 100 kPa pre-consolidation stress. But the true pre-consolidation stress is quite a bit higher, as you can see by the yellow dots. And so that has a huge impact on your conclusions in your geotechnical site characterization, where you're going to recommend, again, driving pile foundations when spread footings were going to be fine. Or it's going to cause you to recommend deep soil mixing and wick drains and preloading when none is needed. So you're wasting people's money and you're not doing your job properly. So it's paramount that you get the highest quality samples that you can for advanced soil laboratory testing. Next. So I put here some references, and you can read these at your leisure, and more detail to be found in these publications. And I think the last slide, yes. So thank you. Muchas gracias. And thank you for allowing me to take up some of your valuable time today.
Thank you so much, Paul, for sharing your knowledge and experience. We have 6 minutes left.
Okay.
To allow some questions. Are
Good.
you up for them?
Yep. Sure.
Okay, so I'm going to ask people to raise their hands if they have any questions for Professor Paul. Here we go. So Thomas, you are muted. Okay.
Thanks, Gail. Thanks, Dr. Mayne, for your presentation. I have a question. If in the quantification of lab sample disturbance,
yes,
for measure the initial void ratio,
yes,
how can I do this in a saturated sample and in an unsaturated sample?
Well, unsaturated soil, yeah, I think both of those methods, the NGI and SQD, are primarily looking at saturated soft clays and silts, I think, for the most part. So unsaturated soil mechanics still has a long way to go, and I don't have a good answer for you. Yeah, it's very difficult.
Any more questions? Emmanuel? Emmanuel Carvajal? You are muted.
Hello, can you hear me now?
Yes.
Good. First of all, thank you very much, Dr. Mayne, for your very interesting presentation. My question, I have a couple of questions. First, what's your opinion about the freezing techniques for sampling?
Yes.
And the other one is, in the case of let's say loose material like tailings with low plasticity,
Yes.
and considerable fines content or silt or clay, whatever. Uh, do you think that it's better to go for CPT testing more than trying to get a very qualified sampling? What's your opinion on that?
Okay, two good questions, and I thought of putting in some stuff about freezing, which is mostly for sands, maybe silty sands even, and gravels. And we've come a long way with that. Yeah, the Japanese started freezing. It's a special type of freezing. It's not a just expose the soil to liquid nitrogen and freeze it. It's a special one-dimensional process where you drive the water out and capture the material at the same time. And it was started out very expensive. It turned out to be at least a $500,000 venture, because each sample costs about 30,000 US dollars, and you had to do at least 12 samples to make it worth your while. That has come down. The Canadians have worked with that. Most recently, Billy Camp in the USA has done that. And so I think if you have some critical projects, that's a good way to go if you can afford to do it. You have to have a very big project to afford it. The device that seems to have increased in popularity over the last 10 or 15 years is the gel sampler. And again, we could have gone into a whole bunch of detail on that. That's kind of a tube sampler, but it has this really gooey gel that helps capture all the soil and hold it together until you can get it back to the lab and then extrude and trim your specimens for lab testing. So that seems to be a more economical, efficient, and it's getting better. So those are two good methods, but they are more expensive, and but I think we're headed that way. Yeah, and then for the tailings, yeah, you have different kinds of tailings. You have sand tailings and you have slimes with a lot of silt and even clay fines. So it is hard to capture silts. Yeah, and it's a problem. Even natural silts, there's still a large group of people trying to figure out how to best sample those. Um, I'm a big proponent of cone penetration testing and other in situ tests. So I think, it goes hand in hand. You take some samples, bring them back to the lab, and hope that you can compare that with the in situ tests. Yeah. They're not one substitutes for the other. They're complements, hopefully.
Thank you. Just a comment, because lately it turns in very difficult task to take some sampling from tailings.
Yes.
So everybody's now relying on CPTs, and it seems that there's not any reference. So we can compare CPT with good sampling, soil. So I feel that there's something to do in that matter, you know, because otherwise we only are relying on CPT, and I believe on all the correlation stuff regarding the CPT, but it's not that easy to rely only on this, you know.
No, it's not. But, you know, if you looked at the piezo cone and a triaxial cell, it's the exact same equipment. You have load cells to measure the axial force, it's axial stress. You have transducers to measure the pore water pressure. And you have, you might have a cell pressure. Again, that's just another same instrument. And then you might have a displacement transducer to measure deflection or depth. It's the same equipment. But, you know, with the lab, you're going to test one perfect cylinder for the same amount of money as you could run a piezo cone and test billions of soil particles down to 30 meters. So it's the same equipment. One, you're testing the ground in its original condition in situ. The other one, you're trying to carefully get samples out of the ground, bring them back to the lab. So we should be getting similar results.
Other questions? Paul, do you have some time for one more question?
Sure.
Seems like we don't have any more questions.
Okay, good. That's always good to.
Okay, so once again, many thanks, Paul. Oh, we have one more question. Okay. You have to unmute, Rafael.
Hello, thank you, Dr. Wayne and Dr. Mayne. Have you heard about the methods to verify the inflection point of the reconsolidation pressure by using the unnatural scale for the consolidation curve?
Is that Jambu's method from Norway?
Yes.
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 Yes. Yep. Yeah, there must be, there are at least 40 different methods of interpreting pre-consolidation stress from consolidation curves. 40. I mean, the most famous one is Casagrande method. That was the first one, 1936. So, but there are a lot more. There's a lot more out there, and you know, depending on what kind of soil you're in, some of them are a little easier to use than others.
Okay. Well, we thank you again, Paul, for your time and for sharing with us. And I also want to thank all of the attendees for taking the time and joining us today. So thank you so much, everyone, and we hope to see you in the next one. Please feel free to contact us. Our idea is to have these webinars, technical webinars, to join us in the technical community. So please contact us if you have any ideas, if you would like to share. We have no problem in collaborating. So yeah, give us a shout. Okay, thank you, everyone. Have a good day, night. Bye-bye.
Adios.